Good morning, everybody. Hope you're having a great day. You're welcome. My name is Hutch Kubu, for those of you who don't know. My job here is to introduce our speaker and get out of the way. So without further ado, I'll introduce Ivan Dedek, who is a brewery bon vivant, man about town, Renaissance man with experience in many different breweries, including Sam Adams, our Jamaica Plains, the original 10-barrel R&D brewery, all the way up to most recently 60-barrel brew house doing about 12,000 barrels a year. So he's going to talk a little bit about brewing chemistry, and we'll see if we can all learn something.
Thank you, Hutch. Hey, everybody. First off, let's start by saying go Heels. Thank you for being out front. This is not going to be overly exciting. I apologize, but anybody who's taken organic chemistry or any sort of chemistry should know that already. It's kind of painful. Luckily, it's not going to be that long, so we're only looking at about 30 minutes. But what we're going to do here is kind of follow carbohydrates from the very beginning, from our barley kernel, all the way through the process until we make alcohol. After that, I'm done. You guys can figure that out on your own. I got this handy-dandy laser pointer to point some stuff out for everybody. And I also want to say that I am not going to butcher every single one of these pronunciations, because that's also what you guys get to do. Because I can't do 6-syllable, sorts of words with multiple numbers in them. So good luck. Let's start off here with a couple of definitions, just to refresh everybody's memories. Chemically speaking, an enzyme, it is a protein. Almost always. It could be RNA in certain situations. Don't worry about that. We're not going to discuss that here. That lowers the activation energy of a reaction. So it is basically like the key to the lock of a door. Can you get in the door without a key? Yeah, you can. It's just going to take a little bit more effort to do so. So that's what this does. It does not actually do the reaction. It's just there to help the reaction take place. It must be at least a tertiary protein. So what we're looking at here is a primary structure, a primary protein. So it's just a string of amino acids. So like something like an insulin hormone would be a primary protein. Then you have a secondary, which are two different types of secondary proteins. You have your alpha helix, and then you have a beta sheet or a pleated sheet. So these are getting more and more advanced. With those, they're going to do more things, obviously, because they're more complicated. One of the things that one of those secondary alpha structures is going to do is something like myosin that makes muscles contract. And then we get to tertiary proteins. These are much more functional. So get to a shape and getting more things. So we're back. This is an actual functional enzyme, is in our tertiary group. And then our quaternary is usually globular, fully functional, things like hemoglobin. So hemoglobin is something that everybody knows, you all have it. It's what makes your blood red. And the reason for that is, in that functional group of that protein is iron. Other animals are not the same way, so hopefully nobody's ever cut open a horseshoe crab. But if you're a psychopath and you wanted to do that, their blood's going to be like blue-green, and the reason for that, in their version of hemoglobin, they have a copper as the functional element there, so that's going to give it that different color. Continue on with some more definitions. We have oxidation. This is a process where a substance loses electron, leading to an increase of its oxidative state. We have reduction, a process where a substance gains electrons, leading to a decrease in its oxidative state. So, Leo the lion goes grr, lose electrons, oxidation, gain electrons, reduction. Easy way to remember that. Yeah. Hydrolysis, a chemical reaction where molecules are split, not necessarily split, but a reaction occurs by the addition of a molecule of water. The next one's pretty important, ATP. Who wants to pronounce that one? Go for it. Good job. Thank you. All right, good job. Yeah, that and pronounce. So whenever we're talking about this, it's the energy of the cell, whether it be yeast cells, human cells. We're trying to create energy, and also we're using that ATP to create other processes. An isomer, this one will come up a fair amount. Molecules with the same molecular formula but different arrangement of atoms. You're just moving placements, whatever, you might have an OH attached to a carbon here and it gets moved over here or changes form. That's basically what isomerization is. So, let's look at malting biochemistry. This is what we know. During the malting process, enzymes are activated that are used during the mashing process to break down long-chain carbohydrates into fermentable sugars. But how do we get to that point? We all know this bit, but here's the nuts and bolts of this. So this process begins in steeping, because the important thing is germination is going to begin at 30% moisture content. So we have to get that barley kernel up to that 30% moisture content. For sustained germination, we've got to be between 38 and 40%. This is going to vary depending on maltsters. So they're going to, certain maltsters and certain varieties of barley are going to vary what they find best. So that's kind of a maltster-driven thing. But the key here is the moisture content and oxygen levels. So we get our moisture content up to that 38 to 40%. We have to get high levels of oxygen. Now the reason because we need high levels of oxygen is without those high levels of oxygen, you're going to just get stuck in this anaerobic state, and you're just going to create lactic acid. You're not going to get all the way through. Now when you see in an aerobic state, it gets all the way down. We produce a boatload of CO2. So we want to get all the way through, and also with the aerobic state, we're only creating one ATP in an anaerobic state. When we get all the way down to an aerobic state, we're creating another one. So the key here is mimicking actual sprouting to basically activate this kernel of grain. So what we're going to do is once the rootlets break free of the, I hate this, thank you. That's going to increase respiration. That's going to allow us to intake more water and more oxygen. So what's actually occurring here is those rootlets are going to break free, increase that, and then our enzymes are going to start to be activated. And the action that occurs is gibberellins and abscissic acid from the embryo are going to get released. This is then going to go to our aleurone layer here. And that's when those hormones are going to start to stimulate the production of the enzymes alpha amylase, endo-beta glucanases, beta amylase, and proteases. So because we're working in now a semi-fluid system, because we've got 38 to 40% moisture in there, and hopefully in the endosperm, those are going to start releasing into that area. Those are going to start to work. Now this whole process is going to work from the end to this end. So this is where, again, we get into a very maltster-driven thing. They've got to know exactly when they're at the exact moisture content they want to be down at the distal end. Because they don't want to, if you're only 18% moisture down here, but you're 46% up here, you're going to have under-modified malt. So slowly, those enzymes are going to release into the endosperm, and they're going to start to actually break down those starches and start sending them back to the embryo. This is going to indicate to the embryo to stop making our gibberellins and abscisic acid. So at that point, the aleurone layer is going to stop creating more enzymes. So they're all in the endosperm, and we've got to basically, the maltster has got to then determine, okay, it's good, our hydration levels the whole way through. Now we've got to actually stop this process and go ahead and start drying. So we've actually gotten one step of our process done here to get from starch to alcohol, and that is creating our enzymes. So these are the two 3D structures. These are both tertiary. So our alpha and beta amylase, none of these shapes are going to make sense to anybody, including me, because I do not deal with that deep of biochemistry. So, if you understand what all those shapes mean, more power to you. But now we've got our activated enzymes, we're going to go ahead and go into the mash. All right, stuff we know here. So warm water and milled grains are combined in a mash mixer. Water activates the enzymes, break down long-chain carbohydrates, amylopectin and amylose into fermentable sugars, glucose, fructose, maltose, and maltotriose. That's stuff we know. So amylose here on the left is a chain amylopectin. So the key here, what you're looking at is amylose is made of completely alpha-1,4 glycosidic bonds. We'll get more into that in a minute. Amylopectin has a 1,6 alpha bond. The difference here being neither of our enzymes can break those. We'll dig into that a little bit more, but and they're usually about every roughly 10 or so sugars in there, and then from there, it stops. You hit a limiting dextrin. So up top here, we know everybody knows our brewer's window thing. Everybody's seen that. And our alpha and beta amylase, alpha basically is going to create larger sugars, 1,4 bonds at random, and then creates a new non-reducing end. And our beta amylase attacks every other, creating maltose and starting at the non-reducing end until it hits its beta dextrin, or this scrolls the other direction. Until it hits its limit. So again, just to reiterate, these enzymes are not actually doing the reaction. So this is an example of beta amylase. It's just kind of holding it in place, and then we've got water coming in to actually break that bond and create our maltose. So let's look a little bit deeper about these bonds and how they work. So as we said, it works from the non-reducing end, which is up here, and it's going to work down and break those bonds this way. So the reducing end, the way to recognize that is an anomeric carbon. You see this here comparatively to the group up here. So it's going to work from that OH group and work down this way. So again, the hydrolysis linkage here, how we break that bond is basically your amylase is going to come in, water is going to be added here, and it's going to break off. So we're picking up that all those hydrogens and the oxygen from that. Here we see 1,4,6 bonds right here. Here's our 1 carbon over to our 4 carbon with an oxygen there, and then our 1,6. So 1 here, down to our 6 carbon there. So again, that bond is not breakable. So we're going to hit a limit eventually of how fermentable we can get to. Now the question is, what if we want to make an ultralight? What do we want to do? So let's say we want to make the most fermentable thing, because generally we can only get to 80 to 85% fermentable. So let's look at how do we want to break this bond. So everybody in here should probably know how we're going to do this. So, amyloglucosidase, if everybody's liking, who's made a brew? Yeah. I still make one. Roots are dead, unfortunately. So an exogenous enzyme that you're adding, either in the mash, you can add during fermentation, your choice. I'm gonna warn everybody now, if you're gonna add this in your fermenter, do it after you crop the yeast, because that stuff does carry over. So just don't do that to yourself and end up with a 0.4 Plato hazy IPA. So this stuff is derived from Aspergillus niger bacteria, built up, and then basically it's used to limit those beta dextrins. So neither of our enzymes are able to get within a couple carbons of where that 1,6 bond is. So this is going to break those down, make you the most fermentable thing you could possibly get to. So now why did we want to do this? Because we want to make an ultralight. Oh, where'd that go? So what we're going to end up with here is basically 5 main sugars. Maltotriose up here, 3 glucoses, maltose, 2 glucose, fructose and glucose, and then sucrose. So about 75 to 80% of your mixture here is going to be these 2 guys. The rest up to 20%, because even with that enzyme, you're not going to get 100% fermentable. It's just not going to be perfect. But the thing is, with fructose and glucose, most of those actually didn't occur during your mashing process. Those were actually already in the barley. That happened during the malting process. They just got broken up in a certain way or were built that way when the barley kernel was grown. So they're actually just there. Your mash giving you those 2 is pretty highly unlikely. So you'll get small amounts of glucose near the end of your mash, but most of it not very much. So let's look at some more stuff we actually know all about. Fermentation. So we're going to add yeast to the fermenter during our transfer, because we have all our sugars. We don't care. We were talking about grain to sugar and alcohol. So yeah, you boiled, whirlpooled, chilled. Now we're adding yeast. So we're going to add 1 million cells per mil per degree Plato. Check with your yeast providers on that information, depending on what you're making and what they like to do. Yeast breaks down sugar, heat, CO2, and ethanol, creates esters, yada, 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 creates off flavors, fermentation 3 to 5 days. Okay, we know all this stuff. So let's look at kind of an overview of here. So this is basically what we're looking at here is we're using nutrients to provide ATP, energy, and in so doing, creating alcohol and CO2. The 2 shown here completed through reduction and dehydrogenase enzymes. We're going to dig more into that. And then, replication, obviously, which we need to complete. So we're going to dig in more to this. These 2 are 2 primary things that we are looking for. So we need ATP, NAD+, and the inverse of those. Without these, nothing is going to occur. So we'll get into more of those right here. So sucralose. Let's see here. Sucralose. Let's look at sucralose again real quick. Because of the shape of this, it can't get through the cell wall. Now, in a weird way, neither can the others. But, so what happens is it's actually hydrolyzed up here. We've got our cell wall on the inside. So it's actually going to be hydrolyzed up in that envelope and not in the actual wall. So it's going to get broken down to glucose and fructose, and then an enzyme's going to carry that across. And then with our maltose and maltotriose, both of those are actually, the enzymes are going to carry them through the cell wall and break them. So we're going to end up on the inside of the cell with glucose and fructose. So this was the easy bit. So now's where it's going to get a little confusing and fun. And we get to have a pronunciation fun. So, I don't know, you nailed the first two. I mean, I'm going to call McManus on the next hard one. So, glycolysis, aka Embed-Meyerhoff-Parnas pathway. So what we're doing here is breaking down our glucose and fructose into pyruvate, which is not alcohol, but way closer than it was. So in step 1, we're going to take a glucose and with hexokinase through phosphorylation and the addition of ATP, we are going to end up with glucose 6-phosphate. So keep an eye on our ATP usage. So we are -1 right now. This is kind of key. So our next step 2, we're going to go to hexosymerase. Close enough. Thank you. And that's going to come in and isomerize that molecule. So no change in chemicals of what the process is, just moving stuff around. And then our next step, McManus, pronounce number 3. No. Phosphofructinase. All right, so step 3. Again, usage of an ATP. Phosphorylation reaction. So we're -2 ATP, so we're down 2 energies. We're down -2 right now. Not good in terms of the cell usage. Step 4, that aldehyde, I can even do that one. A hydrolysis reaction. So something very, very key happens in step 4. It splits. So we no longer have one unit here, we have 2. We end up with both of these. So, Scott, go ahead and pronounce that. All right. All right, Adam, let's go with that one.
Dihydroxyacetone phosphate.
All right. It's as good as I can do. Anybody want to pronounce the other one? Yeah. Glycerolaldehyd?
That's a G3P, everybody wants that.
3-phosphate. So when this process actually happens, you're getting both those. But the next step of our process can only actually work with this one. So step 5 is again just isomerizing that molecule into that molecule. It's just moving the phosphate around so we can get to there so that next enzyme can actually do its thing. But after step 4 going forward, remember we have 2 of these now. So from step 6 on, each of these is doubled. So this process from step 6 all the way through is now 2x. So it's happening twice because we split that. We're in a smaller carbon chain now. So step 6, Gerald, glyceraldehyde 3-phosphate dehydrogenase. So I actually nailed that one. Come on. Kind of a weird one here because you're looking at dehydrogenase, but we're calling it a phosphorylation reaction. It's kind of a bit of both because you can tell here we're pulling out 2 hydrogens, but we're bringing in a phosphate. So, and we're going to get to that 1,3-biphosphoglycerate. Again, next step, kind of a key one because we're bringing in ADP, and ATP's coming out, but it's twice. So we're back to a net 0 after step 7. So phosphoglycerokinase, which is basically a hydrolysis reaction to get to our 3-phosphoglycerate. So again, happens 2 times, so we're back to an even on ATPs. That's kind of key. Our next step 8, phosphoglyceromutase, Mutase kind of gives away the type of reaction it is. If you're going to see isomerase mutase, it's nearly always an isomerization reaction. It's just, that's why you learn Latin. Getting us up to step 9 here, which is, step 9, we're going to pull out some water. Inlase is going to do that. Condensation or a dehydrolysis reaction to pull that water out, getting us down to the, I can't even read that one. Anybody want to read that one? Come on, somebody's brave. Come on, read it. He got it. There you go. All right, so, and then again right here, ADP turning into ATP 2 times. So at the end of this whole process, step 10, we've got pyruvate kinase, hydrolysis reaction, getting us to pyruvate, and we're at a net 2 ATP, which basically means this whole process can get us back to here because we're plus 2 on ATP. Now, awesome, we made plus 2 ATP. Here's the thing that you're not going to want to hear. Yeast don't want to be in here because if they're in an aerobic system, they're plus 28 ATP to go through that process aerobically. So be nice to your yeast because you're making them do stuff they really don't want to do. So, treat them well. So we're here at a plus 2 ATP and we've got to get to, almost there. We're almost there. Almost there. So, but we've consumed all our NAD+. And it's got to be restored because we used it in the earlier process. So in order to do that, we've got to get these final 2 reactions completed. So we've got our pyruvate decarboxylase. We're removing CO2 here to get to our ethanol. So almost to alcohol, but alcohols all end in OL. So our final step of our process, alcohol dehydrogenase. Again, we're getting NAD+ back. That can then again get used earlier in the process, and we can continue to do this. So we have finally reached ethanol. Yay. Here's where things can go wrong, because pyruvate's used in a lot of other processes, so lactate dehydrogenase. So you get to this point, and you have lactobacillus in your process. Lacto's going to do the same thing and just leave you with lactic acid, and you won't get alcohol. So making sure you have a good clean ferment is key. This is also obviously the exact same process that, cramping comes from. Lactic acid in muscles. You get to pyruvate, and it ends up as lactate. We did it. We went all the way from a grain of barley to alcohol. So there's a lot of steps there. I skimmed over a couple of them, but that's knowing this background chemistry can help you out, because understanding all these underlying issues in the chemistry make your life a heck of a lot easier when you're trying to troubleshoot. If you understand that, you're not seeing good solid fermentations and you know this process, there's ways around that, like understanding the chemistry. So, any questions? I told you it'd be short and boring. Huh?
31 minutes.
I told you. I said 35. I know. Yeah, because Josh is here nailing them all, making me look like a dummy.
Oh man, my boss is even worse.
Yeah, I'm sorry. I can't pronounce that stuff. Yeah. Well, that's it. I'm sorry.
Anybody have any questions? All right, round of applause for Ivan. Everybody, thank you so much.